In the previous case, we have seen the equations of the rotational motion of a planet around a star. In that case, the condition was that the mass of the star is huge compared to the mass of the planet, so that the center of mass of the star and the center of mass of the system are very close. But suppose we don't have that condition and we assume that the masses of the two bodies in the system are comparable, then both the bodies revolve around the center of mass of the system. So before we do that, let us just look at the equations for once. We had in the earlier case uh, these equations. The tangential speed v is equal to square root of g m over r. Here m is the mass of the body at the center about which the planet or whatever other small body is revolving, and omega, that is the angular speed, is equal to square root of g m over r cube. Then we have the period of revolution, time t is equal to, find the square of the period of revolution, t square is equal to 4 pi squared over gm times r cube. And if we want to find the frequency of revolution of the planet, in that case, f is equal to, we can use the expression 1 over t. These were the equations we have already obtained. So now we will take the case where the masses of the two bodies are comparable, or we cannot ignore the mass of the body which revolves around the body at the center. Now, in that case, both the bodies would revolve around their common center. So let's have that case here. Let's have an illustration of the case. Here, this is the first body. We can write this m1 having a mass m1. All right. And we have a second body in here. It could be either lighter or heavier or massive, less massive. It doesn't really matter. But in this diagram, we have brought the second body is having less mass, of course, but not significantly less. So here we have the body system. This is a two-body system, M1 and M2. Here, need not be the same mass. Both the bodies need not be the same mass. As the figure shows in here, M1 is massive compared to M2, but not huge. So we can just write, just for the convenience, M1 is greater than M2, but not too massive. In that case, both the bodies will be revolving around the center of mass of the system. So let us assume that this is the center of mass of the system. Okay, so we write this as center of mass. Now, the distance to the first body, let us assume that in here, from the center of mass, we can write it as R1, this distance. So this is the separation between the center of the first body, M1, and the center of mass of the system. We write it as R1. And similarly, the separation between the center of mass and the center of mass of the second body, we can write it as R2. So this is R2. Now you can see that R2 is greater than R1 because M2 is less massive than M1. So this is R2. And the total distance between the two masses, let's write this as R. Obviously, we can write two relationships. The first one we can write R1 plus R2 is equal to R. That's obvious. Now, the second relationship that you can write is about the equation, about the center of mass, the equation for the center of mass. We can just write this equation M1 R1 is equal to M2 R2. Now we may be able to write both the R1 and R2 in terms of R. For example, look at this equation. Let's put this as equation number 1. Watch here what I'm going to do now. This is equation number 2. This is just a little bit elaborate thing. So we will see the relationship between R1 and R. So we will see what is the relationship between R1, R2, and R. So look at here. From this relationship, look at the second equation. We can write, from the first equation, we can write R2 from 1. 1 means equation 1. We can write R2 is equal to R minus R1. Now, if you substitute this third equation, let's call this as equation 3. All right. If you substitute equation 3 into 2. So you would get M1 R1 is equal to M2 times, instead of R2, you may write R minus R1. So it becomes R minus R1. So we just expand this right hand side further. You will get M2 R minus M2 R1. Now we can rearrange the equation to find out the value of R1. Watch how I do it. Take this M2 R1 to this side. So you will have R1 common factor. You will get M1 plus M2 times R1 is equal to M2 R, or rather R1 is equal to, this is important, M2 over M1 plus M2 times R. So this is one equation, R1. Similarly, we can write R2 is, just give it a little bit more space so we will find it easy. We can also write here, here you have a multiplication, okay, right? Similarly, we can write R2 in terms of R. R2 is equal to M1 over M1 plus M2 times R. So these are the two equations where we get the values of R1 and R2 in terms of the masses and the separation between them. So let's call this as together equation number, let's say 4, because this equation may be used further in the derivation if you want. Depends on your need. Okay, now let us consider the second part of the relationship. We are going to find out the tangential speed. So, okay, we'll just do it now. Okay, so let's call this part as A, okay, or one. So this is the first part. This is one. All right. Now let's go to the second part. The second part we will describe, in this case, we will describe tangential speed, tangential speed, angular speed, angular speed, and period of revolution of a two-body system, period of revolution. Let's take a look at the case again. I'll draw the diagram one more time. So we will find it easy to work with these quantities. So let's take a look at it. Now draw the diagram again. Same diagram. Here we have the first body whose mass is m1. Here we have the second body whose mass is m2. And this is the line joining the two bodies. All right, here we have it. And this mass is m1, which is greater than m2. And then we have the center of mass somewhere here, center of mass. And then we have this distance marked r1. Let's have all the everything, and this distance marked as r2, and the separation between the two bodies as r. So let's have r1 here, r2 here. Okay, put the arrow in here. So what happens in this case is that both the bodies will be revolving around the center of mass at the same angular speed. So let's work out the relationship now. So again for m1, or you can write for m2. Let's do it first for m2. Either way you can do it. I'll use a different color because it doesn't look very nice. Let's do it in here. This is a little bit. Okay, let's take the case of m2 for m2. Once you get the equations for m2, you may get the equation for m1. Just by looking at them, you can guess the equation. You can say, again, you use the same idea. What is it? The gravitational force provides the centripetal force. So we can write the force FCP. FCP is equal to Fg, and we can write here what is FCP and Fg. You can write, for example, Fg will be acting in this direction, both the sides. M2 will be experiencing a force Fg. In this particular case, this is the direction of Fg, and on M1, this is the direction of Fg. So we are considering M2 first, so we need to consider this one. So you can write m2. Let's assume that the tangential speed of the second body is v2 over the distance between the point about which m2 revolves with m2, that is r2. r2 is equal to the force of attraction between the two bodies is gm1 m2 over r square. This is the relationship. From this, we will get m2 and m2 will cancel out. Here, r2, mv2 square upon r2, and here it is r, so you cannot cancel, but instead m2 and m2 can be cancelled out. So you will get v2 squared is equal to g m1. Then what we get, this r2 square, r2 will go up, so you will get r2 over r square. R square can be written as, you can write r square itself. So further on we can write this is g m1 over r2, oh sorry, and r2 over, you can write r square as r1 plus r2, so you can write r1 plus r2 whole square. Now if you want to change it in terms of r, the numerator r2 in this part of the equation, if you just use the r2 value from the relationship 4, you may get a relationship irrespective, independent of r2. You want me to do it, I will do it, but this equation would be sufficient for your calculations because we will do it as two segment calculation. The first part we can calculate earlier and then we can calculate it further on. Look at this part of the equation. I can work on further using this relationship. What is R2? R2 is equals to M1 upon M1 plus M2 times R. So you can substitute that R2 value into this equation. Here substitute the R2 value, you will get, okay, here this can be further written, V2 square is equal to gm1 times r square. You can keep it down here just for convenience, we can rearrange them again later. R2 can be written as, what is the R2 relationship here? Look at the top. R2 is equal to m1 over m1 plus m2 times r1. So let's say R2 is equal to, what is R2? All right, so you get the equation here. What was that? M1 R plus M2. So here we have the relationship. Instead of R2, or you can write R square here. What we had, M1R divided by M1 plus M2. So you can write M1R over M1 plus M2. Look here. Here, R and R would get cancelled out. You will get the relationship G M1 square over M1 plus M2 times R. This is the relationship you will get. Now let's try the second case. The V2 square is equal to Gm1 square over M1 plus M2 times R. So we can write V2 is equal to, change the color. 2 is equal to square root of g m1 squared over m1 plus m2 r. Okay. Now, using the same idea, we can write v1 is equal to v1 is equal to, and instead of m1 square, you will get m2 square. So, square root of g m2 square over m1 plus m2r. Now here, you must remember r is actually the separation between m1 and m2. Well, you don't need to by heart these equations, but you need to know how we got these equations. Now we will try to find the equation for the angular speed with the same idea. You don't need anything new in here. Let's find out angular speed. So let us call this B. Use a different color. Okay. So we write B. Angular speed of M2, the second mass M2. Let's call this as omega 2. Now actually you don't need to do it separate because the angular speed for both the bodies in a two-body system would be the same about the center of mass. Now we can write the equations the same way as in the earlier case, equating the centripetal force to the gravitational force. So we can just write for M2, this is for M2, FCP is equal to Fg. The centripetal force is given by not in terms of the tangential speed but in terms of the angular speed. So we will get the expression as, because the mass is m2, you should write m2, and then we will have the r, so that will be r2. Of course we can write omega 2 squared. This is the equation you already know for the centripetal force. That is equals to g m1 m2 over the separation between the two masses r squared. This will be the expression. Now m2 and m2 would cancel out and we will get the expression omega 2 squared equal to omega 2 squared is equal to r2 will come into the denominator in here. So R and R2, you should remember R is equal to R1 plus R2. You must remember that expression. So this will be M2 and M2 cancels out. You will get the expression G M1, and what we have M2 cancels out. Denominator you will have R squared R2. R2. Now we can find the value of R2 from the earlier equation. You know, we have that equation at the beginning. R2 is equals to M1 R over M1 plus M2. So you can substitute that value if you want. M1 R upon M1 plus M2. So instead of R2, you can write here R2 is equals to M1 R over M1 plus M2. So you substitute that value, you will get omega 2 square is equal to g m1 over r square. Then we can put this value in here. This will be m1 r in the denominator, and on the numerator you will have m1 plus m2. So I can stretch this line a little bit farther. It will be m1 plus m2. Now let's simplify this equation. M1, what will this? Oh, it's M1. So this is M1. Okay, fine. M1 and M1 get cancelled out. R cube is in the denominator. So what will be left in this case is G times, you will have M1 plus M2, and in the denominator we have only R cube. Now look at this expression here. This expression is symmetric about, or rather same for R1 or R2, because neither R1 nor R2 is in the equation, and M1 and M2 tells that both the masses come in the equation. So we can just write omega 2. That will be exactly the same as omega 1. That is equals to, what would be that? Omega 1 is equal to, you will have the expression, you need to take the square root. The expression will be G times M1 plus M2. Right, this will look like, okay, let's stretch this a little bit, over R cube. So the angular speed will be constant for both the bodies. That is something you should remember. Listen here. Here we are measuring everything with reference to the center of mass. You must remember that. So now we have all the expressions here for the V1 value and V2 values are given, and we have the expression for V1 and V2, V2 and V1, and then we have omega 2 and omega 1. Then you can commonly you can call this as omega, because for both the you can call this as omega because angular speed remains constant for both the bodies. Now we can find out the period of let's say revolution. The period of revolution will be the same, of course, so we don't need to do it for separate. Period of revolution t. We get the expression for period of revolution t. Of course, t is equals to 2 pi over omega. So we have this expression, t is equal to 2 pi over omega, or we can write, we imply that t square is equals to 4 pi squared over omega square. We know the omega value. You square it, the square root will get removed, and then you can see that R cube will go to the top. So you will get the expression. Gm1 plus m2 come to the denominator, so you will get the expression t square is equals to 4 pi square over g m1 plus m2, g times m1 plus m2, m1 plus m2. So 4 pi square, then you have r cube in the numerator. R cube in the numerator. Again, you can see that this equation will be the same for both the bodies. The period of revolution will remain the same for both the bodies. So these are the set of equations you get for two bodies revolving about their center of mass under gravitation. Of course, you can combine the equations together if you want and try to remember, but it will be always advisable for you to learn how to work this out rather than learning these equations by heart. It's not a good idea. That's all.